Hello, so this is my module 3. I decided to do random coefficient modeling, otherwise known as linear mixed effects. Firstly, I want to talk about the differences between standard linear regression and random coefficient modeling. So Friedman states that regression models are used to make causal arguments and is a dominant paradigm. For regression models, we need to have an initial theory that specifies specific variables of interests, and we also need to look at interactions. We can estimate our parameters given the model. So linear mixed effects models, according to Bates et al., states that parameter estimates can be determined by LMER functions in R. So we want to look at fixed and random effects. We also want to look at REML, which is restricted maximum likelihood. So the core differences between standard linear regression and RCM are basically the parameter estimates. These parameter estimates could be the slope and the intercept, and they vary across distributions. And modeling variances are not just for the means in RCM. So LME, this function, otherwise known as LMER in R, calculates the means and tells how much variance there is between the mean and the grand mean. So for standard OLS, it assumes that there are observations that are independent across time. So RCM handles cluster data. And we can use this cluster data by using interclass correlation, ICC, and like I said, it measures the degree of the clustering and the proportion of the total variance. So, like I mentioned before, there is fixed effects and random effects. Fixed effects is basically the overall mean of means, and random effects is how much variability there is between values. So, we start with a simple model and then we compare more complex models as we go along for linear mixed effects. We also want groups by class, and we have the desire to get these means. So I decided to use a data set involving speed dating. This data set was pretty large, and I decided to use extracted variables of interest such as participant ID, which is given to each subject, gender, age, race, attraction, intelligence scores, and likability. So I chose to do um, race as an IV as well as attractiveness, and likability is my outcome. I also included here gender and intelligence. I just decided that maybe I might use it later for analysis, but I didn't actually use it, but it could be used in the future. So let me tell you more about this data set. This data set basically was taken from Fisman and Leininger from Columbia, and they decided to look at gender differences in mate selection. And they believe that there is evidence from speed dating in regards to mate selection. So they decided to look at demographics, dating habits, self perception, and the overall values that they see in a mate. So I decided to do dummy coding for my means of coding. I decided to do this basically because I saw that race was a numeric variable that was given and assigned in the data set. We have Black, White, Latino, Asian, and Native American and other, and one was given to Black, two White, three Latino, so on and so forth. So basically, changing a numeric into a categorical variable is what dummy coding aims to do. So basically, I chose Black as the base. I could have used White, which probably would have been more sufficient, but I chose Black just because it was the first variable that was used and one was assigned to this. So here we have our contrast. We have Black, White, Latino, Asian, Native American, other, and we have our assignment of one, and then it goes down the line here. And then we also have the summary of race that was in the overall sample. We have NAs here basically due to probably a loss of data or data that was not computed or put in correctly. And here we have like basically a nice little plot of the overall variables. So basically overall there were 6 Black participants, 20 white, 23 Latino, 26 Asian, 18 Native American, and 7 other. And basically, dummy coding was used sufficiently, and I decided to separate these columns out. And the reasoning for this is that continuous variables are typically used in OLS. And yeah, so then I decided to do a regular and standard linear regression model for this. I chose likability as my DB, like I said, and then race as my independent variable that I recoded. And then I basically ran the regression, and here is the output shown. We have our residuals, our coefficients, which shows our parameter estimates, our standard error, and our p-values here, less than 0.05. We also have our overall residual errors and our multiple r squared, which is 0.009, which is extremely low. And we also have our adjusted r squared. We also have our p-value here, which is less than 0.05, showing that it's significant, but our variance is extremely low. So then from here, I show some diagnostic plots. We have our normal QQ plot, which shows our outliers on the tail end. We have our residuals versus fitted plot, our scale location plot, and these basically show heteroscedasticity. And we also have our residuals versus leverage plot, which includes Cook's distance. So from there, I decided to do random coefficient modeling, and basically I added first likability onto and regressed it onto just the subject, and this is like our standard, more simple model. And we also have REML, like I said, which is restricted maximum likelihood included. So basically, if they're we have our residuals, our scale residuals as well. We have our random effects and our fixed effects, which is what I explained before. So overall, we have fixed effects that show our overall mean and means. Here we have the number of observations, 8,137, which changes. And then we also have our p-value here in our fixed effects section of the output. And here we can look at the correlation matrix in the plot. And this is basically like over time how basically each section or category of race is plotted over time. Or of likability, I'm sorry, of and subject. And then I also chose to look at interclass correlation coefficients. And basically ICC, if it is above 0, it is highly problematic. And here we have 0.01, which is above 0. So, and then I decided to do an ANOVA in R as well. And this was for the third model that I will be showing. But for my second model, I basically included race as a variable. And here you can show the difference between Black, Latino, Other, and White, and the p-values are shown here in fixed effects, as well as the correlation effects of each race, and they give 4 as standard. And then we also have our random effects as well. Number of observations is seen to be 8,072. And so for my ANOVA table, basically this is for the third one, in which I included race as a nested variable. And here is what it looked like for the variable nested. We have our number of observations here too. We have our differences between random effects and fixed effects similar to the other model shown. And basically, what I aimed to do was add complexity to the model. I decided to start small and then add more variables in. For my last model, I decided to do a fourth one to add even more complexity. And this included the variable of attractiveness. Basically, overall attractiveness that was rated from the participants were included. So you can see it down here in the random effects. And similarly, we have fixed effects as well, and our p-values. So here's our overall plots. We have the one where I included just race. The next one shows the inclusion of race nested, and then the next one shows the inclusion of attractiveness. And basically, this is just correlation matrices across time. And this is also fitted as well. And so basically, there are several implications that I can discuss. One would be I can have a more sound initial theory that I can draw from and use for future studies. And I can also play around with other variables within the data set. I can look to see and have a better hypothesis about what will actually produce an outcome of likability. So I can also include gender, like I said before. I can include intellectual ratings, and so on and so forth. And I can basically add more complexity to the model as we go along. Um, and that is my module 3.